After all this philosophy, let's now go back with our 2 feet firmly on the ground. I'm going to do the next lecture, Exploring the Deep. It's a very large lecture because we are traveling billions of light years in this particular lecture. I certainly don't want it to get boring, but we will start with our neighborhood and then we will get further and further. But I'll definitely only do the first part tonight. I'll just open the handout in case we will need that. So now we are going to travel and we are leaving our Milky Way galaxy. So I could have named this course Leaving the Milky Way instead of Leaving the Solar System. But as I explained, it has a different name. But we leave the Milky Way and we look in what we find around us in terms of galaxies. At some point, we realize that individual galaxies don't really matter anymore. We see that they are organized in groups and clusters. Another scale up is in superclusters, filaments, and walls. These are the very large scale structures of the universe. This is basically the excursion that we're going to make. And if we want to figure out or imagine where we live in that universe, we have an address which is called planet Earth in the solar system, in the Milky Way galaxy, and now we're going to add more lines to our universal address. This is an important diagram, which is from a website by this guy here called fantastic quasi three-dimensional images. I use them all the time. This is what we call our local neighborhood. So what you see here is the Milky Way galaxy. You see the dwarf galaxies that I discussed last term. Some of them are a little further out. This is basically the volume that we have been discussing in the previous course. But now if we zoom out, and the scale here is, I'm looking for the scale, it's not in here, but it's about 10 million light years across. Then we will see another big spiral galaxy. It's the famous Andromeda galaxy. It's almost a twin of the Milky Way. I think it's a little bit larger. The discussion is going back and forth on that, but it certainly has more stars than the Milky Way. And the third, in terms of size, galaxy, which is also a spiral, is the Triangulum galaxy, which is here. It's a much smaller than the other two. So those are the main players in this block. And then the Andromeda, and somehow together even with the Triangulum galaxy, because they are in each other's gravitational influence, you have a number of dwarf galaxies around them. So I'm going to discuss the Andromeda, I'm going to discuss the Triangulum, and then we are going to look at some of these dwarfs around them. That's our first step into the universe. If you live in the northern hemisphere, you can see the Andromeda on a clear night as a little fuzzy patch. It's a naked eye object, but you need a very clear sky. On the northern hemisphere, you don't have very often the clear skies anymore because of the aerosols in the upper atmosphere. I know that I've lived most of my life on the northern hemisphere. When I came to New Zealand, I'd never seen blue skies like you see here. It was really an eye-opener. Anyway, let's not go there. But it is a naked eye object, although very, very fuzzy. We can occasionally apparently see it here from New Zealand in the northern sky, very low in the northern sky, but you need a certain type of the season, type of year. I don't got to the top of my head what is the best time. You can look that up. But it's very low at the northern horizon for us. in New Zealand. If the stars in the galaxy would be, and the Andromeda would be much brighter than they actually are, we would see the entire visible part of the Andromeda in our sky like this. It would be several times larger in diameter than the full moon. Just imagine if these stars just would be a little bit brighter, well, a little bit, quite a lot brighter, or the galaxy would have less dust in it or whatever, then this would be our view of the Andromeda galaxy. Wouldn't that be spectacular? The diameter of the galaxy is 220,000 light years. Again, this is, and you know that now because we've extensively talked about it in the Milky Way, with respect to the Milky Way, that some people say it's 100,000 light years diameter, then they say it's 200,000 light years. There's all kinds of different estimates, and then when you include more halo stuff, it becomes a lot bigger. So the traditional size for the Andromeda is 220,000 light years. Whatever that means. This is a fairly close-up image. It has been made by an amateur astronomer. This is a photographic object if you're interested in astrophotography. There are two companions. This one here, which is in our point of view behind. This is a galaxy in its own right, small one. And here's another galaxy on our side. This is called M32, and this one is called M110. Remember, these are the Messier designators. It's in the Messier catalog. 31 is the Andromeda itself. Or in the new general catalog, it has the number 224. The galaxy itself in mass is about the same as the Milky Way, but it is a bit larger. Even the visible part is a bit larger. It certainly has more stars. The estimate is it has 1 trillion stars. Our Milky Way, if you remember, the suggestions range between 200 and 400 billion stars in our own galaxy. And it has about 500 globular clusters. So it is our big brother, you could say, our big neighbor in the local group. This is an experiment I did myself, because the view angle to the disk is about 77 degrees. That's not really very favorable to study the structure of the spiral galaxy. It clearly is a spiral galaxy. You see those lanes, those dust lanes. What I've done with this image, I've just stretched it vertically in Photoshop with the cosine of 77 degrees to pretend that this is an image when you look at it top down. Of course, that's completely fake. This looked like a barred spiral, but as we will refer to it later. But it's just because this patch here is now stretched out. I did that. It's an artifact. But anyway, it gives you an idea that we are really looking at a spiral galaxy here. Very similar to our Milky Way galaxy. In different wavelengths, as always, in astronomy, things look differently. That's why multi-wavelength astronomy is so important. These are different infrared ranges. The Spitzer Space Telescope was a very famous infrared telescope. This is mainly dust. That's dust that is heated by nearby stars, so it radiates in infrared, heat radiation. Heat is very low temperature. I mean, the space is very close to absolute zero, and this is just a little bit above absolute zero. That's what we call hot infrared astronomy. But it is heat radiation. That's why we see this in infrared. Completely different image than when you look at the visible one that I showed you before. Even a slightly different wavelengths in still infrared gives you different components here. Blue and green are the stars. Now you can see individual stars. And the glowing dust in between is the pinkish color here. Anyway, so we can study this structure in different wavelengths, and we can draw our conclusions of that. Here you see immediately what we can do with other galaxies, which we cannot do with our own galaxy. We don't have this bird's eye view of our own galaxy. I've repeatedly discussed this in the previous course. We are inside, so we can only see so much. But here we have a fantastic object of study where we can see our nearest neighbor, which is this is the closest galaxy we have to study as a whole. And it is very similar to our Milky Way. So this is a fantastic opportunity to do galactic astronomy, if you wish. This is a famous image by Hubble. It's a mosaic, which is only part of the disk of the galaxy. There is a zoom tool here where you can see the whole thing. Just absolutely amazing what the Hubble can do. But this is the nearby galaxy, 2.5 million light years. We call that nearby. So we can study this in great detail with the equipment that we have. That was already the Hubble Space Telescope. I can zoom in here. You see that you can see individual stars and how many there are. This is not fake, this is just actual images. There are different resolutions that come up when you zoom in, but these are actual observations by Hubble. This is where it stops. But you see that these are all individual stars. Different colors, which tells us about temperature of the stars, and probably, and if we use spectral information, of course, we get a lot more information about these individual stars. It's quite clear that there is a lot of star formation happening. We see similar structure as we see in our Milky Way, the dust lanes. There's a spiral structure, maybe not as distinct as in supposedly in our Milky Way, but still a very distinct. To go back to my slides, distinct structure, spiral structure. Go back to previous images here. You can see here these dust lanes. This is really a spiral galaxy, there's no doubt about it. And there's also the coloring. You can see there's a lot of star formation happening. It's very similar to our Milky Way. So our Milky Way and Andromeda are very similar in that context. They also must have the same age. I'm now extrapolating just Alain Provost thinking about this, that the age of the Milky Way and Andromeda will be similar, because we are in a similar stage of our evolution. There's still a lot of dust and gas inside the disk for star formation. We'll talk later about different types of galaxies, and we'll see that there are galaxies that don't have any star formation happening anymore, because they don't have that stuff, the dust and the gas anymore. Everything's used. We only have old stars, a whole collection of old stars. These are the so-called elliptic galaxies. We'll go there. So the Andromeda is clearly in a very active spiral galaxy. There are black holes in there. This is in X-ray. Black holes, you know that now. They when there's material falling in via the accretion disk, that gives a very high energy radiation, in particular X-ray. And this is a way we can find black holes, because you can't see black holes, obviously. You need to look at the smoking guns, so to speak, of material falling into the black hole. That's what makes them identifiable. These are stellar black holes. So these are my big stars that have exploded in a supernova explosion, and the core has collapsed into the black hole. So these are very massive stars. So these are, it starts in the center with this. These are various regions here that we have in X-ray, we can find these sources. There must be a supermassive black hole in the center as well, just as we have, like we have in our Milky Way galaxy, or maybe even more than one, because in X-ray we find different sources. And in a certain time, when the Chandra X-ray telescope was looking at it in 2006, there was another source appearing. That's this one here, or it's one of those two. So in addition to here, we found a flare of a new X-ray source. That can only be that there was a relatively large amount of mass falling into that black hole and then radiating and flashing up. Since then, it will have disappeared again. Must have been a timely transient phenomenon. Generally, that supermassive black hole or those supermassive black holes are relatively quiet, just like our own Milky Way. I discussed that. There are galaxies where you have enormously active supermassive black holes, name is M87, which we talked about in terms of the Event Horizon Telescope image. I'll come back to M87 when we travel further into space. That's a very active galaxy which has a supermassive black hole. One of the largest that we have ever observed, which is very, very active. There's a lot of material falling in, a lot of interaction happening. But the Andromeda, similar to the Milky Way, is the supermassive black hole in the center is relatively quiet. Sorry, I'm rolling my mouse. This is an image which I showed you at the end of last term's course. When we were talking about the Milky Way, we are here. And I mentioned that we have studied the halo of the Andromeda galaxy, which is in the center here, by looking at quasars, very deep sky objects. That's not to scale. These are very, very powerful radio sources, which are fluctuating as well. And because we look through this halo in different directions, we could make an estimate of the angular size of that halo around the Milky Way by looking at the background objects. This is how we got an impression that the so-called halo, which causes this effect, has a diameter of something like 2 million light years. What I mentioned in the previous course, and that's why I already brought this up, is that we will have a similar halo around our Milky Way. We have observed Cepheid variables which are about 1 million light years away. They're clearly in the gravitational influence of the Milky Way, so they belong to us, to our system. And which means that, and that is why I brought this up already last term, that the two galaxies, if you include the halos around it, material that belongs to that system, we are basically touching each other as neighbors. So let's look at some of the dwarfs around the Andromeda galaxy. First, we have this one here, M32, and then we have M110, as they are named. You could compare these with the Magellanic Clouds of the Milky Way. These are satellite galaxies of similar size, actually. M32 is 6,500 light years. The Magellanic Clouds are about 15,000 light years across. So this is about half the size of one of the Magellanic Clouds. This one is larger. This is larger than the Magellanic Cloud. Not much, but a bit larger. significant about this, it's a fuzzy galaxy. It's not really a particular type. But this is because it will have passed through the disk of the Andromeda Galaxy already. It has been disturbed by tidal forces. It's kind of a hodgepodge. There's no clear structure. I discussed it with the Magellanic Clouds last term, that the original idea was that the Magellanic Clouds already had passed through the Milky Way disk, but we now know that this happened. These are new visitors, both the Magellanic Clouds. But this one very likely has already gone at least once through the disk. These are all in gravitational influence, of course, of each other. So these satellites, they are orbiting basically the center of the galaxy itself, which means that at some point they will go through the disk region. The M110 dwarf is kind of unusual that we find. It's also very disturbed in structure, but we find star formation happening in the center. There are young stars in there. And that would mean that this is undoubtedly the consequence of some sort of a merger, some sort of a collision that has happened. There's activity happening. Very similar, by the way, to the Magellanic Clouds. If you recall the story about the dwarf galaxies last term, around the dwarf galaxies around the Milky Way, most of them are kind of inactive, no star formation. But the Magellanic Clouds, they have lots and lots of star formation happening inside of them. It's a bit similar here with the M110, the dwarf, undoubtedly. This is a famous discussion topic. If we do Doppler measurements, the shift of the spectral lines, the spectrum from Andromeda, we see it blue shifted, means it comes towards us. And it's coming towards us with, do I say what the speed is here? Yes, 110 kilometers per second. So if I speak this sentence, the Andromeda is already a few hundred kilometers closer than when I started. It's 2.5 million light years away, so don't hold your breath. It's not coming here anytime soon. And this is the whole point. We have new information about the Gaia from the Gaia satellite. And the traditional idea, you can find still many places that discussion is that at some point we will have a fantastic view in our sky where the Andromeda and our own galaxy will meet up in a collision. It's never a real collision, physically speaking. It's a merger. Stars, the distance between stars is still very large between individual stars, but they go through each other. But it is the tidal effects and the distortion because of gravity, which makes it a fantastic light show. And this would be very special in our sky if we would still be alive. The point is that based on the new estimates, this is going to happen in about 4.5 billion years from now. If you remember our story about the evolution of the sun in our solar system, in about 4.5 billion years, it's over for the sun. It will have become a red giant already. The Earth may or may not have been swallowed up in the large red giant that the sun has become. And shortly thereafter, shortly in terms of maybe 0.5 or 1 billion years later, the sun will, the core will collapse in a white dwarf, and the rest of the sun will disperse into space in the shape of in the form of a planetary nebula. So by the time that this is now predicted to happen, based on the more accurate both position and velocity observations, also the direction of the velocity, based on the new Gaia observations, we now know that this is going to happen later than originally thought. And now if you do the math, or you just look at the numbers, 4.5 billion light years, there may not be a solar system anymore by the time that this happens. The galaxy will be there, Milky Way, yeah, sure. But there's nothing, there's no life form here that could possibly observe this. This is a diagram based on this new information. So it will not be a direct merger in any way. They will pass each other at something like 400,000 light years distance, the first pass. And then, of course, there will be a dance based on gravitational influence. And eventually, and then you talk about billions of years later, there will be a merger. So it will end up in the one galaxy which already has a name. They gave it Milkomeda. I can't say that I like that name, but it doesn't really matter. This is going to happen when there is no solar system anymore. That's my point. There's a video here on YouTube, which is still based on the original estimate that it would happen earlier and that it would be more or less a direct encounter. So I'm sorry to disappoint you, but it doesn't really matter. It's going to happen so far in the future, there won't be anything to observe this here on Earth, at least in our solar system. Okay. The other one is M33 Triangulum. Here you see a close-up by the Very Large Telescope in Chile. You immediately see that this, not only it's a spiral galaxy, but there's a lot of star formation happening. It's all these red patches. So it's a very active galaxy. We see it in a more favorable view angle than the Andromeda. That's just an accident, of course. It can't do anything about it. 54 degrees. It's about 1 million light years, a little bit less away from the Andromeda. And it will be something less, a little bit less than 3 million light years away from us. But there is a heck of a lot of star formation happening. I mentioned the Andromeda has star formation, like our Milky Way has star formation happening. Very similar. This also, but it has more intensive. But it is a smaller spiral galaxy, but clearly a nice spiral structure. In the triangular galaxy, one of the brightest patches of star formation is the famous I'm not sure if it's famous. It's the nebula NGC 604. If you do astrophotography, then there's a famous object. This is an enlargement here by the Hubble, where you see a core where there's a lot of light, which means there are very bright stars that recently have formed, a typical situation of star formation. Very massive stars happening to have formed and still are forming. They're pushing away the material. You get all these arcs here. It's similar to the Tarantula Nebula in the Magellanic Cloud. This is what I was thinking of when I said it's very famous. It looks like the Tarantula, but it's a much bigger. This is 1,500 light years across. There's one nebula here. Is in this part here. Compared to the Orion Nebula, which is another famous star formation region close by our planet in the Milky Way, it's 40 times bigger. In X-ray, there is a large binary near the center, which has a stellar black hole of about 16 times the mass of the Sun. We know it's binary because it's eclipsing. So we can't see the black hole, but we can see the companion. And we see that the companion is blinking with a very short period of 3.5 days. So these are very massive stars. One of them is already a black hole, which are very close. So they're orbiting each other extremely fast, period of 3.5 days. But those are stellar this is a binary system. It's a stellar black hole. There's no evidence in Triangulum of a supermassive black hole in the center. Now, if I'll load the image on the internet. So it's this one here so that I can make a reference. This is very large. It will be very difficult to navigate. But I want to keep this as a reference. That's this image here. Let's look at some of the dwarfs of the Andromeda. First, NGC 6822, which is this one here. This is just an arbitrary sample. Not arbitrary. I looked at some specific characteristics of different types of dwarfs. This made that selection. If you talk about all these individual objects, it gets really boring. IC10 is an outlier here in this direction. 31909. Let me go to the bigger image. Oh, wait a minute. It's this one here. Yeah, of course. It looks like it belongs to the Milky Way, but it's actually in the very likely in the still in the gravitational influence of the Andromeda. You need to see the depth in this image. So this is 3109, and we will look at one of the sextants as well. These are really outliers. It's disputable if they are still really in gravitational influence of the Andromeda, or if they have exceeded escape velocity. That's very hard to say. And then the Tucana dwarf, which is on this corner here. Just a sample of some of these dwarfs. 6822 is at a distance to us of 1.6 million light years. This is the whole thing here. There are some enlargements you can look at in detail. These are clearly areas of very intense star formation which are happening. But the overall structure is a little bit of a bar structure if you have the fantasy to see that. These pinkish areas are especially the so-called H2 regions, which is ionized hydrogen. The atom has been, or the electron has been stripped because of intensive radiation in that area, and then the electron can be captured again, and you get this these emission lines in the hydrogen alpha color. So that's these are very distinct in this image of that the whole dwarf galaxy. But it is later we'll talk about classification of galaxies, but this is irregular. You cannot say that there's a spiral structure or something. But kind of vaguely we can see in a bar here, if you wish. IC10 is the one that's lying in the kind of in the outskirts, in the upper right direction in the diagram. It's also irregular dwarf. It's only part that we can see of it because it's in the more or less in the plane of the disk of the Milky Way. So it's on the other side for us here on Earth of the Milky Way galaxy. The visible part is about 5,000 light years across. It has a large, even visible gas halo. There's a lot of star formation happening here. It's even referred to as star burst. I'll mention that later again. Star burst means an excessive amount of star formation happening, and that usually is the result of a merger. That objects, in this case probably two dwarf galaxies in the past, they are actually merging right now, and that stirs up so much of the material in terms of density waves, etc., that you get an excessive amount of star formation, provided, of course, that the dust and the gas that stars are made of is available, and that is definitely available in this dwarf. So I would say, I haven't studied this, but you can look it up. IC10, it's a famous dwarf galaxy, but it's very likely they were an ongoing merger. And there is another X-ray binary that you can find there. It's a black hole with a big companion that has about 30 times the mass of the sun. And then the 3109, it's in the upper left corner of that diagram I showed you. This is really in the outskirts of the local group. We see it almost edge on. It distinctly looks like a spiral galaxy still. And probably the smallest really spiral. All the others are more irregular structure. It has only first generation stars. You can see that from the metallicity. If you recall discussion about stellar evolution, or in different contexts I've talked about metallicity. Astronomers talk about metals, everything above helium in the periodic table. It's a very confusing term especially when you're a chemist, and metal means something entirely different. So anything above helium. The reason for that is that the original universe, when matter was formed out of energy, and I'll talk about it later in the Big Bang theory, the universe only had time to form hydrogen and a little bit of helium. That was all. Then it was game over because the temperature dropped because of the expansion. I'll explain that. This is a fantastic reconstruction very shortly after the Big Bang. But the point is that we know that the original material in the universe is hydrogen, 75% roughly, and 25% helium. That's it. And if you cannot find any higher elements, that means that these stars are made of that original material. They never have gone through other stellar cycles which have enriched the gas and dust out of which new generations can form. This is why we know, you recall the first term in this year when we talked about the solar system and the sun is probably a third generation star because we have uranium here on Earth even. There's one of the highest, the largest atoms that must have formed in major events in the past through different cycles of star formation, stellar evolution. This particular galaxy is devoid of any higher elements. It's only hydrogen and helium. You can see that from the spectra of these stars, of course. But that's interesting. It's pristine material from the original universe. We find many planetary nebulae, which means there have been very many sun-like stars. And it forms a subgroup in the far upper left corner of that diagram with the sextants A and B and D Antlia dwarf. Let me show you the thing again. It's this group here. So we talked about NGC 3109. And then you have sextants and the Antlia dwarf. These are really in the outskirts of what we call the local group. And this is then one of the two sextants dwarfs. It has also profuse star formation happening. Again, there must be something happening, like in terms of a merger or so. The whole thing is, and it's only 5,000 light years across, it's not that big, but it's the whole thing, it looks like one giant supernova explosion. So there's so much massive star formation, and then after millions of years, they run out of material, so they collapse as a supernova explosion. And very likely a lot of black holes. So that's happening in this dwarf galaxy. So it's very active. The big yellow blobs are stars in the foreground. Don't belong to the galaxy. And then we have finally the Tucana dwarf, which is in the bottom of that diagram. this one here. Should switch on my. Oh, well, there's a pointer doesn't work on that one, of course. So this is Tucana. It's kind of a vague image here. This is made by Hubble. And these are only old stars. There's no star formation happening, which is really an exception compared to all the other dwarfs in the local group. Many of them, most of them are really active, which means young in astronomical sense. These are all old stars, but there's no star formation happening. Actually, there was a similar to that spiral galaxy I showed you before. The other dwarf which I showed you before, which is composed of only old stars. So this one is a blob of, I'm not sure what the metallicity is of these stars. Anyway, this is the exception that it doesn't have star formation happening. Because this is far away from the other major galaxies. It's in the corner. This is an ideal object to study dark matter. And when we look at the motions of stars, then we can estimate what the total gravity effect is in this whole blob. And then we definitely see that these motions of these stars, especially in the outskirts, cannot be explained by the visible matter only. There must be a very large component of invisible gravitating matter that causes these motions. This is the typical discussion we've had last term about dark matter. I'll come back to dark matter in the context of cosmology and the history of the universe. So this is a study object for dark matter. Now I've reached the point that we will talk about groups and clusters. I was thinking about stopping here, but it is still more than 10 minutes to go. So I'll just make a start, and I'll probably pick up here next week to have an overlap, because I don't want to push and rush through all of this. But if we now go further than our local group, then we look at distribution of galaxies in different directions, which is not uniform anymore. Well, the local group itself was not really uniform, was it? We had these concentrations of the Milky Way and the Andromeda, etc. But if you look in the bigger picture, and I'll show you the diagram in a minute, in a few seconds, then we will see clearly a structure. There are regions of fewer galaxies, and there are regions of dense regions of galaxies, and they form groups or clusters. I've looked at tried to find definitions of groups and clusters, but they are kind of the same. So I think these terms can be exchanged. I prefer the term, like most people do in those literature, in those articles, of the term clusters. These are groups of galaxies that clearly are in each other's gravitational influence. And now it's not one major galaxy in the center and then dwarf galaxies around, but no, these are really major galaxies, each of them in their own right, and they form clusters. So that's the next stage that we go into when we zoom out from where we are, from our local group. So basically, we're not talking about individual galaxies anymore from this point forward. Here you have an image that I have enlarged. I'll discuss this first. So this is the next zooming out, if you wish. Let me read the text here. These clusters contain, up to thousands of galaxies. And because our over time our measurement of distance has improved so much since those early days of Henrietta Leavitt and Hubble I talked about. That has made a major impact on our understanding of the structure that we are actually looking at. This is the larger version of it. So we are here in the center. This is the local group. You see, it's no discussion of Milky Way or something anymore. We don't talk about individual galaxies. Each of these designators that you see is a cluster of galaxies. The biggest one in our neighborhood, if you still call this neighborhood, this is about 100 million light-years, I guess, across. This is 10 million here, this bar. The biggest one clearly is the Virgo cluster. But then you have two other major clusters in the more or less opposite direction, the Fornax and the Eridanus, both more or less in the same direction seen from us. And we have a number of smaller groups. You see now the term group comes up, but these are, I don't know, it suggests in this image that the term group is for smaller numbers of galaxies together, and clusters are bigger. It's not really an interesting distinction. Don't worry about that. I call them all clusters. So this is the area where we're going to investigate now, and we'll look at some of these clusters in more detail. Of course, we can study the gravitational effect, and because of the motions of the individual galaxies in these clusters. And at this scale, we see exactly the same thing we see all the time. There is a very large component of material stuff that has the gravitational effect. We call it dark matter, but we can't see it. It doesn't interact with electromagnetic radiation in any way. There's no way to detect it other than through its gravitational effect. Remember, we talked about dark matter extensively in the previous course. But here we see the same very dramatic conclusion, is that if we explain the orbits, the motions of individual galaxies in these clusters, the visible material is something like 5% only of the gravitating effect, which means mass. 10% is X-ray emitting gas. So with X-ray observations, we can find that there's a large component of X-ray emitting gas, which means that that's gas that is heated very extensively with because of high energy processes that are happening, and they radiate in X-ray. That's even twice as much in terms of the gravitational effect. And then 85% is unseen. That's famous or notorious dark matter. So again, at this new scale now that we zoom out to, you see exactly the same problem that we have. We are missing something very, very major in terms of its gravitational effect. We have, of course, not only ideas about measurements of individual galaxies in each of these clusters, but we can also see how these clusters themselves move through space. And if we extrapolate this to 1 billion years from now, then this image will have to be remade. It will slightly look different. So anyway, the major clusters that we are going to talk about are Virgo, Fornax, and Eridanus. This is a close-up of the Virgo cluster. What you see here in the center is M87. Does that ring a bell? I mentioned it earlier tonight as well, made a reference to it. This is where the Event Horizon Telescope has made an image of the supermassive black hole in this large elliptic galaxy. It's a red color, that means it's an elliptical galaxy. I'll talk in the next lecture more in detail about the different classifications. But elliptical means it's all stars. It's not, there's no star formation happening. But there is a supermassive, you can call it a super duper massive black hole in the center of M87. M87 is actually in the center of the Virgo cluster. It's a very famous cluster because of that supermassive black hole, the biggest supermassive black hole that we have observed. I'll come back to that. The blue ones are spiral galaxies, like our Milky Way. You see that in the center, most of them are red colored. They are mostly old elliptic galaxies. In the outskirts, like here and here, you see many blue dots, which means these are younger galaxies. These are spirals, and they have star formation happening in them. But it's the overall picture of the Virgo cluster. There's about 2,000 galaxies inside of here, and with 15 million light years. You can also identify subclusters, different groups, if you want to use that name. So here you have an actual image, which is annotated of the central region only. You see M87 here. You see a very similar one, 89. You see that Messier has been observing those with his telescope, and he made that catalog. These are all M numbers. So he just saw that these are fuzzy patches, but now we know that they are galaxies, of course, in their own right, and that they are galaxies inside a large cluster of galaxies that we call the Virgo cluster. You can click on these links here. Let me just go there and have a look. It's a zoomable version. See if there's a version. Oh, here. Yeah, okay, now we can zoom in. So this is when we take a real accurate image. This is probably from the Hubble. No, ESO. Well, could be Hubble, could be VLT. But you can zoom into these individual galaxies in this cluster. Here you see an example of a spiral galaxy. This is probably M87 in the center. So this is what we call an elliptic galaxy. You see them in all kinds of details. It's really interesting to spend some time on this image and to just play around with it and to see what kind of a collection of completely different galaxies, types of galaxies that are all combined in this cluster. But the key thing here is that in the central region, most of these galaxies are what we call elliptical galaxies, and they are basically not, they don't have any star formation happening. And in the outskirts, we have the blue ones, which are active star-forming spiral galaxies. So you see where we are now. I'm stopping here, but you see where we are now. We are not talking about individual galaxies very much anymore. We now are going into the range of clusters. And from here on, it's getting bigger and bigger through the rest of this lecture, where we will talk about not only clusters, but clusters of clusters, or there are terms like filaments when they are stretched out like long streets, filaments, and we also talk about voids, which are underdensities of galaxies in certain regions. And then we will go towards the overall structure of the universe. This is the journey that we are making in this lecture.